So hello guys and welcome. So I thought I should talk about like 20 platforms that I worked on. So basically I was kind of working on the game that I ported to a lot of platforms, and I thought that I should talk about it. Now, the game itself is a bit on the trollish side, so I guess I cannot really mention it here, but I still thought that it was worth mentioning and talking about what I learned on each platform. So we're going to start first with the ColecoVision. So this was the first version of the game that I made. And this one was nothing special really. I just used like a toolkit that was provided by the so-called Bienvenue. He has since changed their name, and I mean I already was familiar with the ColecoVision because I already made other games for the platform. The trick is I never really made a game that was constantly updating frames, so basically full motion video, and so that was the trick. But basically I found out that you can actually update the VDP fast enough to get full motion video. It's something like 6 FPS or so, and that was sufficiently good enough for the game. Now, on this version at least, I did not use PCM playback, even though this platform is actually capable of. And I was also using something called the Mega ROM chip, which allows bigger ROM cartridges. So I could have the space for like sampled voices and stuff. But I didn't do it on this ColecoVision version at least. And let me show you the code real quick. Uh, I, so hold on a second. So this was the Coleco version of it, and as you can see, it's mostly straightforward. We have a main loop, uh, and then we have something called switch game mode, and we set up default values. And you may notice that this is basically how it works for like static images. So I would basically load the pattern for like how it's laid out, and then I would just I'm not sure if it's here actually. I think it's another text file which is called game. But yeah, for the text it's mostly trivial actually. So, and when I am using graphics from another bank, I just do that instead. So I have multiple C macros, and I have to call that C macro before I can call the graphics and put it into memory. So that's how you do ROM bank switching in C with the ColecoVision. So it's nothing too special really. We're going to talk about the next platform, which is actually quite similar to the ColecoVision, and it's the MSX2. Now, originally I wanted to make like a direct port of the ColecoVision version, and that meant actually only supporting the MSX1, because the MSX1, besides the memory and the BIOS, is, and actually the sound chip, which is slightly different, it is very similar. It is the same VDP video chip. It is the same processor. And yeah, I mean, those two platforms are so similar that they got ports to each other. So quite interesting. But the MSX2 was more capable, and the most notable addition was the so-called Mode 5, which added 16 colors, and also I believe the sprites were also 4 colors as well. On the ColecoVision and MSX1, you could only have sprites up to 1 color. You could have sprites with a bit like on the Atari 2600, where each scan line is its own color. But besides that, you cannot go really around that, and it's not really useful, to be honest. I've only I only saw this being used for games like Radius, for example. So which scan line is a sprite color. I've seen that. But yeah, and the MSX2 also has plenty of memory. And to be honest, it was actually quite a pleasure to work on the MSX2 because we also have, unlike on the Colecovision version, official ROM bank switching support. So we have open source designs, and this is basically how the MSX2 version looks like. It is mostly similar to, for the most part. For the PCM voices, which was the first version for the MSX, because the Colecovision was the first port of the game. But then when I worked on the MSX2, I thought it was worth adding voice, speech, voice and stuff. And on the MSX2, you can do that thanks to something called PCM Enc. So PCM encoder, basically. And the sound quality is actually pretty good. I've shown this in my other video. And the size is also pretty small, despite the fact that it is only at 8,000 hertz also, and 8 bits also. So yeah, I was quite surprised by the quality of the speech. The VDP on the MSX2 is also interesting because you can issue commands. Now it is still very limited. You can only do like copies and clearing operations, as far as I know. I'm mostly using like the clearing stuff. But besides that, I mean, this was pretty smooth sailing for the most part. The only issue that I encountered was actually related to ROM, because if the ROM ends up being too big, it cannot work with like the official hardware. Now, I've been told later that it does work with homebrew cartridges, but I wasn't sure at the time, so I just basically completely took out the MSX2 Plus code and the MSX1 code. So the game ended up being only for the MSX2. So a bit of a shame, but eventually I may do an MSX2 Plus version of it or not. So yeah. Next, we have the ZX Spectrum, more specifically the 48 kilobytes, well, the 48K, should I say. This was released in, it was mostly sold in Great Britain and stuff. They also sold a few units in the US as the Timex Sinclair, but it wasn't successful there, so mostly due to strong competition by Commodore. But yeah, I mean, it is a bit annoying. I mean, on paper, it is not that good, but I think it's not too bad for what it is, especially for the price. But yeah, I mean, it was very clear that despite the improvements that it got over like the ZX 81, which was even more terrible than this one, it felt really primitive, to be honest. And despite that, I didn't have a lot of issues. And it was the first time that I used compression for the graphics. So I used ZX1 for compressing the frames, and it was fast enough for like decompressing them on the fly. However, there is a quirk with the MSX, with the ZX Spectrum, my bad. You have to also update the color table, and when you do that, if you're not fast enough, that causes graphical glitches. So unfortunately, if you don't want to do that, your only result is to either have a faster algorithm, so something like RLE, or you just do a mem copy. And maybe I should have gone with RLE on the ZX Spectrum because the end result was a bit messy, to be honest. It still works for the most part, but yeah. And I also considered going with cartridges, but we only have like 16 kilobytes to work with, so I gave up on that idea as well. It was just better to load everything into memory and have the game run from memory instead. So let me take a look at the code real quick. I mean, it's nothing spectacular, to be honest. So this is the ZX Spectrum code, and well, we have the loop with the switch. You may also notice the this. So this is quite specific to the Z88DK SDK, and that basically reduces like the size of the function calls and the performance stuff and those. And I didn't have a lot of bytes left for the game, so keep that in mind. And luckily, in the case of Z88DK, we also have plenty of provided functions for like text and even for like decompressing frames. So on the ZX Spectrum, I was using something called like the ZX1 Agile RCS, which is much slower than just ZX1. But the compression was much better. So I only use that basically for like static frames, so the title screen and the cutscenes. If you take a look at the frames in game, we have to update both the pattern, but also like the main stuff basically. So yeah, it's graphics on the ZX Spectrum is actually divided into two parts. Because one provides the graphics but without the colors, and one provides the color in the color table and stuff. So basically pattern and color table, that's how graphics work on the ZX Spectrum. It's a bit quirky, to be honest, but it makes sense given how they designed it. And it is somewhat partially backwards compatible with the ZX81, so that could explain the design decision that they made. But we're gonna take a look at other platforms that handle this much better. So that was the ZX Spectrum. So let's take a look actually at the Sinclair QL. So this was the successor to the ZX Spectrum, except that it was one of the first computers ever to come with the Motorola 68000. However, this one is a bit particular. It is the Motorola 68008, and this is an 8-bit variant of the processor. So the external data bus is 8 bits, and that considerably slows it down compared to the normal Motorola 68000. However, despite that, it is much faster than the normal ZX Spectrum. And we also have the benefits of the architecture and the features that it supports, unlike the Z80. So don't be fooled by that. So despite the fact that it is twice as slow as it is, really, it still ends up being much faster than the ZX Spectrum on a clock basis. Graphics, I would say the graphics are an improvement because, first of all, we do have the option of a higher screen resolution, even though it doesn't make a ton of sense on this computer. So 512 by 256 with only 4 colors, or if you want to have more colors, you could have 256 by 256. So this resolution is a bit strange. But I think they made the right decision here. I mean, the screen buffer is only 32 kilobytes, and this computer is fast enough to do a mem copy to that, basically, thanks to the main CPU. The sound, however, is pretty bad. So basically it talks to a microcontroller, which also handles the keyboard. And we only have one channel of sound and only simple bits, and that's it. I mean, I would say it is worse even than the ZX Spectrum, because you cannot do PCM playback on this, because the microcontroller isn't fast enough for PCM playback. So yeah, and the revision that you see here, the first one, it only came with 128 kilobytes of RAM, and 32K is used for the screen RAM. And actually, if you want to use two screens, half of the memory is already gone. And some of it is also used by the OS. So this computer also came with the multitasking OS. However, it didn't have like a GUI, unlike the Macintosh, which was also released during the same time. So it was not a very good comparison, despite the fact that it is multitasking. And yeah, I mean, it is capable, but it is a very poor gaming machine. And the joystick also implemented a bit weird. So basically they're mapped to the keyboard keys. And if you want to handle the keyboard, as I said earlier, you have to talk to the Intel 8049, which is the microcontroller that I was talking about, and also handles the sound, a very primitive sound, I should say. Let me show you the code for that one real quick. So nothing special here again. There is one piece of code that is very specific to the Sinclair QL, and that is the music code. And I actually use ChatGPT to actually help me with the music playback stuff. Because if you take a look here, actually it was here, I believe. Oh no, actually it is. Yeah, I believe it is a function, an official function as part of the OS stuff. So I was a bit confused. So basically we just go through like a C array, which is right here, and we just play the music through that. And here we also tell how long the music is, so that it then loops back when it is over. There's also something interesting here. These two lines right here are, it is for enabling something called supervisor mode. And if you don't do that, the basic interpreter will still run in the background. So it is very crucial that you do that as well. And also make sure that you set the resolution to low. I also have another C macro to set it to high, which is the 512 by 256 resolution that I mentioned earlier, but it is only like 4 colors, so I didn't go with that. You may also notice that I'm using the upper memory area as temporary space for stuff I do. And I mean, I was really starving for memory on this machine, so that's why. So yeah, that was the Sinclair QL, quite a quirky computer. The VSmile. So this one is also special. I won't show you the code for that because it's nothing fancy, and we're still making progress into like the homebrew VSmile stuff. But basically, it is a 16-bit Sun Plus processor, and you have to use a compiler for that. And it has only 20 kilobytes of RAM. It does support external RAM, and it is mapped onto like the upper RAM portion of the memory, so that's good. It also supports PCM and ADPCM sound. Now, at the time that I made this game for the VSmile, we had no idea how to do sound, but eventually someone else figured it out, but he has not posted the code for it yet. So yeah, I will update the VSmile version with sound once he figures that out. It supports high color, 8 bpp, and also weirdly enough, 6 bpp. And this sounds like a huge pain, so that's why I stuck with 8 bpp, and it looks nicer, to be honest. And so the VSmile, now you may wonder how can it do high color with only 20 kilobytes of RAM? Well, what it does is it holds just the memory for one scan line, and then it just fills that up and just copies the image scan line by scan line. Now you may think that this would be very slow. However, surprisingly enough, it is actually very fast at doing so. In fact, I could probably do like 100 frames of just graphics on screen per second on this VSmile. So I wouldn't worry about that. And that was in high color, by the way. So yeah. And as I said earlier, there's no frame buffer. But if you do need a frame buffer, there is the option of using an external RAM. But using external RAM increases the cost. So most games did not use like external RAM, except for one, which was a graphics studio game. Now I said that I would not show you the code, but actually let me show it to you. So yeah, we have all of the hardware registers for updating the stuff on here. And if you take a look at something called like draw sprites, it is basically just like I said, really. So we do it scan line by scan line and just update the pattern and like the color pattern. I mean, I forgot the exact details. There's like an attribute map, and then there's the tile map that we have to update. And I also have this function for initializing the 8 bpp and high color mode. And there is also a text. I mean, the 2 bpp modes. You can in fact have one layer for text, which is 2 bpp, and then have another layer for graphics, which would be 8 bpp or even high color. I use 8 bpp in this case. But yeah, I mean, it's just a loop and we go through all of it. Now, there's also another issue. The controller, it works for like a minute, and then after a minute, it doesn't work anymore. So we're still working on figuring that out, unfortunately. But unfortunately, the game can be finished in under less than a minute because it's kind of a troll game, as I said earlier. So yeah. So this one is a Soviet computer. This is the BK Electronika, also called BK0010. And this one came with the 3 megahertz 16 bits PDP 11 CPU. Now you may think that because this is like a 16 bits processor clocked at 3 megahertz, it would be very fast, but you would be wrong. And the graphics, they're also not very impressive, even for like the time. But the Russians, they didn't have like anything much better, and that was in like 1984. So I would say that compared to like the Sinclair QL, it's not too bad. But it is obviously far inferior to even the Sinclair QL. So 256 by 256 and 4 colors, which is what I use for this game, and only around 16 kilobytes of RAM available, and the other 16 kilobytes is used for the screen RAM. We also have a sound beeper, which is actually just the cassette port. You can do PCM playback through that, though I was not using PCM playback on that PC due to lack of space. GCC surprisingly supports the architecture, although it is extremely buggy. I ended up just sticking with 0.0.0 to get the game working, because otherwise I would get strange glitches. I looked at the assembly and it just didn't make any sense. So let me show you the port, well, the code for it real quick. I do use ZX0, I believe. No, ZX1 actually, because if I'm not wrong, yes, I also use ZX1 for the frames, and this is the reason why it is so slow, because I mean the architecture, it's not very fast to begin with, and we also have not a whole lot of memory. If you, as I said earlier, the screen RAM is 16 kilobytes, but we only have 16 kilobytes including the graphics for the whole game. So not only I had to reduce the window of like the graphics, but I also had to ensure that the graphics were compressed, because otherwise this would simply be not possible. So yeah, this thought was quite interesting. So this is probably one of the strangest computers that I've ever worked on. So I mean, it was still worth it, but yeah. So the next computer is this so-called Lvov PK01 computer. This is actually a Ukrainian computer. You can still find them on eBay. And this comes with an Intel 8080 compatible CPU. It's actually a clone of it. It is clocked at 2.5 megahertz. We get full colors at 256 by 256. And we can change the palette. In fact, we have a huge selection of palettes. I believe it is like over 100 palettes available. But like the colors, they're all strange. I eventually ended up with a good, well, a decent selection. But yeah, it doesn't work like the other computers. The palettes, they're like hard coded. So we have like over 100 palettes. Yes, sure. But yeah, it's hard coded. So yeah, 48 kilobytes of RAM and 16 kilobytes of VRAM, which is part of the RAM, or of the 48 kilobytes of RAM. Now, this computer has an annoying quirk. So the VRAM is not mapped directly onto the upper portion of the memory of the address space. So basically what it does is, if you want to write a pixel on screen, you have to disable the lower portion of the RAM, so that the 16 kilobytes of VRAM would get exposed. And then you would copy the graphics to that. Now, unfortunately, because of this quirk, I ended up having the game fit onto 16 kilobytes of RAM because of this quirk. Now, the most ideal scenario is that I would copy the graphics to a temporary buffer, and then do the copy again to the VRAM. But I was afraid that this would be too slow, so that's why I stuck the whole game onto like the upper memory portion that was still available when you enable the VRAM. So let me show you this. So this is what I'm talking about right here. So the moment that you enable the VRAM, so here's a clearing video RAM code, for example. Once you enable it, you can clear the VRAM portion, which is now located at 4000. And then when you disable it, that portion of the VRAM gets disabled, and we're going back to the available RAM. But that means that if you have stuff stored on the lower RAM portion, then this code is inaccessible. So you must make sure that you don't use the lower portion of RAM if you do stuff with like video memory. I mean, it is extremely annoying, unfortunately. So yeah. So the PMD-85, again, this is an Intel 8080 CPU. This time it is slower. Black and white graphics at 288 by 256, although there are actually color upgrades, which this computer does have, and my game does use as well. 32 kilobytes of RAM and 16 kilobytes of VRAM. It only has a monitor OS, so just enough to load a game from tape. And I have to say that unlike the other computer, this one is straightforward. So VRAM is onto the upper portion of the address space, and all of that 32 kilobytes of RAM is available to you. So no bullshit that you have to do with like the VRAM. You can just do a mem copy to C100 or so. So let me show you the code actually. So yeah, this is how you just do a mem copy to like the video RAM. It is very straightforward. I was quite pleased to see that finally a computer that was not utterly strange. I mean, most of the Russian computers were completely strange and annoying to work with, and I even have like the memory map that I put on here, and as you can see, the video RAM is in the upper portion. So finally, the designer of it were not completely retards or whatever. They're not what we, but yeah, they had a brain. So it was quite pleasant to work on this computer, and even the color extensions are backwards compatible with the black and white screen of it. So basically, you can have color graphics, but if you have a PMD-85 that doesn't have the color upgrades, no problem. You can still run the game in black and white. So very cool to see actually. So pretty nice computer to work with. This one, however, it is probably the worst computer that I've worked on. So the Exidy Sorcerer. This was released in 1977. Yes, and this come with the Zilog Z80 at 2 megahertz and 8 kilobytes of RAM. Although I've seen conflicting sources on that. Some say it is only 4 kilobytes. MAME says it is 8 kilobytes, so I went with that. So 8K it is. Text-based display. This was a pretty nice text-based computer, but however, there were no graphics. So you had to emulate a graphical display using the text layout, and that means that each letter or whatever, or like character was 8 pixel by 8 pixels. So assuming that we take the XD resolution into account and we divide it by 8, so 512 divided by 8, that's 64. So you can emulate a bitmap display by using each character cell as a pixel, and that would get you a resolution of 64 by 32 pixels. But most games that I've seen did not do that. They simply redefine the character set in order to have higher resolution graphics. And I did not really do that for this game. I simply ended up using like the high-res resolution that was provided with Z80 DK. And then I simply ended up using the lower resolution for like the in-game stuff. So let me show you the code of it. So for like the next ports up until like the Oric version of it, I was using the Exidy code base as the basis for the ports onwards, because as you can see, the entire game was fitting on like less than 300 lines of C code. So that's why I ended up reusing that for the other ports, simply because I could quickly port the game to other platforms this way. So the next one is actually quite similar to the Exidy Sorcerer and was even inspired by the Exidy Sorcerer. So this is the Excalibur 64, and the name is actually a nod to the Exidy Sorcerer, and that's because it shares a lot with it. So in Australia, the Exidy Sorcerer for a while was actually, I would not say popular, but it had a following. And 2 years later also, they released the Excalibur 64 for like 400 Australian dollars as a kit, because as you can see here, the user was expected to make their own keyboard and case for the computer. So not exactly for like newbies, should I say. The upside, unlike the Exidy Sorcerer, is that we do get colors, 16 colors in fact, and a lot more memory, so 64 kilobytes of RAM. But unfortunately, it is still business oriented, so it is still text based. There is still no sound, not even through the cassette port, I believe. And yeah, it was just very primitive, which is unfortunate. So let me show the XCD. Oh, well, not the. This is the Exidy Sorcerer version. This one is the Excalibur 64 version. It is quite similar to the XE version of it. However, for the graphics, it is a bit different. So you see, as I said earlier, it has 64 kilobytes of RAM. So how do we write to the screen? How does it get mapped onto the on like the 16 bits address space? Well, you have to, like on the Lviv and Lvov computer, you have to do a call to enable the video RAM portion, and then you only get like I believe it is 8 kilobytes of RAM available onto like the upper RAM portion of the computer, and then through that 8K of RAM, can you copy the graphics to like the video memory, which gets actually mapped onto the lower portion of the RAM. So this shares like a very annoying quirk of some of the computers that I worked on. So what I did in this case was I copied the ZX1 buffer to the upper portion, and then I will have the ZX1 decompression code store on that, and then decompress it from there. And that's how I managed to have animation and stuff on this computer. But yeah, it was very, very annoying. But despite this, due to the fact that it is text-based, it is very fast at updating graphics, as long as you can figure out how to work around this and the quirks of this computer. So the next one is the Oric 1 and the Oric Atmos. So this was released in Britain as a response to the ZX Spectrum. And the specs are quite interesting. So it seems that they learned from the mistakes of the ZX Spectrum. So the processor is not Z80 based. It is a 6502 processor. The first Oric only came with 16 kilobytes, but there was also another version with like 48 kilobytes. The graphics is the more interesting bit. So 256 by 200 resolution and 8 colors. Now you may think that, well, this isn't hugely impressive, you might say. However, the color cell limitations are better on the Oric because on the ZX Spectrum it was only 2 colors on like a single cell, so 8 by 8 pixels. On this computer, the color limitation is actually more like 6 by 2 pixels, that you can have 2 colors, so it's actually less limiting. And besides that, I mean, I think, in my opinion, that if you compare against like the Oric 1 graphics and the ZX Spectrum, there's no contest. Like the Oric graphics look so much better because of that. And it only takes like 8 kilobytes of video RAM space onto the upper RAM portion of memory. On the ZX Spectrum, it was something like almost like 7 kilobytes, and it looked much worse. So for an additional 1 kilobytes of VRAM, the Oric one looked much better. And we also have a 3-channel PSG sound chip, unlike on the ZX Spectrum. Now the downside is that most of the code for that sound chip, it pretty much assumes a Z80. So if you want to do like PCM playback and stuff, you have to basically make your own code, because it's not going to work on this. And because of that, they actually sold quite a lot of Oric computers, and it was quite cheap as well. It was over $100, which was also the price of the ZX Spectrum. But unfortunately, they still failed, because do you see those specs? They never changed in the following models. It stayed the same. So the computer was stagnating, and sadly, that's how they died. So let me show you the Oric 1 code, which I also ended up using as the basis for the following ports, because again, it is quite small, and I also made a few additions. So I'm using this BSD code, well, the BCD code, my bad, for like the high school. And if you take a look at like say here, so as you can see here, in game we're only actually using like 8 kilobytes of VRAM, and the lower portion gets used for text. So that means that I can fit in more stuff onto the memory. Now you may wonder, why didn't you compress the frames? Because this does take space after all. But I only ended up using compression for like the static frames, as you can see here. And the reason is simple. So you see the 1 megahertz CPU? That's why. The 6502 CPUs are terrible for like decompression and stuff. They are much slower than even the Z80 is with like ZX1 and stuff. That's what I noticed anyway. I mean, this, in my opinion, the Z80 clocked at 3.5 megahertz is much better than the 6502 clocked at 1 megahertz. For the 6502 to actually be decent, it needs to be clocked at least like 1.8 megahertz, which is only a few computers are. So stuff like the C16, for example, or the Plus 4. But this computer, it never got the CPU increase, so a bit of a shame. So the next one is it's not actually a computer or a gaming console. It's the TI-83CE. This was the successor to the monochrome TI calculators, and it was the first device to use the so-called EZ80 processor clocked at 50 megahertz. It supports 256 colors at 480p. Now, high color is supposedly possible on this, but I believe it is something like 12 bits rather than 16 bits. And the CSDK that I was using for this, it didn't support the high color mode, at least not at the time that I was making the game. and we only get like over 100 kilobytes of RAM. We do have plenty of flash ROM space that we can use to push onto the screen and stuff. But yeah, I mean, besides some strange issues that were not really related to the SDK, it was mostly my lack of experience with this calculator. It was mostly straightforward. Besides that, so let me show you the code for it again. So quite similar to the Oric version actually, because as I said earlier, that's what I ended up using as the basis. But I kind of cheated on the TI-83 version. So yes, I am using compression here, ZX0. Now, why did not use ZX1 instead of ZX0? Well, the CPU it's a lot faster than the Z80 processors that I'm used to. So on this calculator, actually ZX0, I mean, it is slower than ZX1, yes, but on this calculator, this makes no difference, and it has better compression ratios than ZX1. So that's why it's being used here. And yeah, and I also have to mention that I also scale up the image by twice. So the resolution, it's not actually 480p in game, it's actually more like half of that. And then yeah, it gets displayed properly and stuff. So let me move on to the next machine. So yes, I did make an NES version of the stupid game that I mentioned earlier. So again, 6502. This time it is clocked higher, which is good to see, even though it did not need it particular. 2 kilobytes of RAM. This is very small, but you have to remember that you can't execute code from ROM, and you can even expand on that through like cartridges with like the MMC3 chip, which has its own onboard memory, and 256 by 240. For NTSC it is 224 for the height, and with 25 out of 54 colors. And we also get 64 sprites, but only 8 on a single scan line. Now, this platform was a lot of struggle, actually. It may seem simple at first, but in reality, it was one of the most difficult platforms to actually make the game for, mostly because of the sheer complexity of the MMC3 and stuff. I mean, the NES was not designed, well, it was designed because clearly you can use the MMC3 and stuff. But initially, NES games, they were just stuck with like 48 kilobytes of ROM, and that's it. So it was quite a lot simpler if you consider that. But now that we have the MMC3 chip, we have stuff like CHR banks that we have to switch back and forth. And I also have to bank in and out the DPCM channels that are being used for this game, because yes, this does use PCM playback, unlike some of the other previous computers that I mentioned earlier, except for the MSX2 version, of course. And yeah, as you can see, I kind of hacked around that. So you may wonder, well, oh, gee, what's with the music init stuff before we do the sample play? Well, you see, this is how we actually load the, how we basically bank in and out the DPCM playback stuff, and along with this as well. And now in this case, I'm actually waiting for like the duration and stuff. So duration is set to here, and it just goes on a loop against the VSync. So that's how I do like the voiced cutscenes. But in game, I'm just using like a PCM stuff without the weights because it is actually hardware accelerated. And as far as I know, it was the first piece of equipment besides the phone to the mass public that could decompress, that sort of had like a compressed form of PCM, and that was also hardware accelerated. So, fun fact. And yeah, as I mentioned earlier, on the NES, you don't have like some video RAM that you can update on the fly. That's just not possible. In fact, the NES is too slow for that. You can only update the name table up to like 300 bytes per second. Actually 300 bytes per frame, should I say, my bad. But during my testing, it was more like half of that. So the only trick to do FMV video on the NES is just switching the CHR banks, and that's how I do it. As you can see here, basically the CHR banks are completely uncompressed, so that's how I got away with that. So that's why I said that the NES may seem simple, but is actually quite tricky. But once you figure that out, it is straightforward. I mean, it is not overly complex. Well, besides that, obviously, but yeah. uh, I wouldn't say it's a fun platform to work with, but it is popular enough. So I thought it was worth doing at least. And I'm glad that I gave it a try at least. So the next one is the Commodore 64, which was also the best-selling computer. So again, we have a 6502 like the NES, although it is clocked at 1 megahertz here. 64 kilobytes of RAM, 16 colors, hard-coded colors, 8 sprites on a scan line, and a 3-channel stage shift. So back in the day, back in like 1982, there was nothing else pretty much that was better than this. This was one of the best computers when it comes to gaming, with like sprites, sound channel, and stuff. Now, for this game, it was actually a poor fit for the Commodore 64 architecture because I said it was a pretty decent gaming machine, but this game is a bit particular because we're updating frames on the fly, and we need a pretty strong CPU for that. And unfortunately, the 64, the CPU is kind of lacking, to be honest. 1 megahertz is not enough. And it turns out that the VIC chip is also very slow as well. And I kind of looked at the demo scene, how they tried to do like a PCM, not just PCM playback, but also how they do FMV stuff on the Commodore 64. And I kid you not, the only example that I found of FMV video on the Commodore 64, it was the moon landing, and it was completely black and white. Now, initially I wondered why, but then when I gave it a try, it actually makes sense because this stupid computer shares a common flaw that the ZX Spectrum also has, but the ZX Spectrum had a better processor and this one doesn't. So, and on top of that, the ZX Spectrum had like a smaller amount of memory to update per frame, unlike the C64. So let me show you the code. So this is how the main code looks like. We're using the multicolor mode. And as I said earlier, I ended up using black and white graphics for this. And in fact, I had to do it in 6502 assembly, which I was not familiar with, and still I'm not familiar with. So Yeah, so basically it's we only get like 4 frames. Uh, these frames were not even compressed, by the way, because if I were to compress it, it would be even slower than that. In fact, even I don't believe like the static frames and stuff were even compressed. So let me show. Let me actually take a look at my code a bit because I haven't touched this code for a while. So yes, I do actually. No, I don't actually. Yeah, I'm actually just using a memory copy for on the 664. And when I showed this to people, they said that, well, self-modifying memory is a pretty bad idea if you want to make a cartridge version of the game, because self-modifying code does not work from ROM unless you copy said code into RAM, which gets quickly annoying. So they advised to me not to do that. But unfortunately, that leaves me with just that. Basically, this is so outside of self-modifying code, this is the fastest way of doing a mem copy. But however, it is much slower than the self-modifying code was, and that unfortunately hurts me in this case because not only that I could not do like compressed stuff, but it just ended up being a poor fit. Eventually, I realized that for the C64, the character-based mode, which unlike the multicolor mode, is only 3 kilobytes large, unlike the 10 kilobytes large, that is for like the VIC-20 chip, because this this size that you see here, that's not even the full size of it. It's more like 8K for like the pattern stuff, and then an additional 2K for like the color cells. So this was too much for the Commodore 64. It still worked though, so not too mad about that. But yeah, this computer, ironically enough, it's actually a poor fit for 3D games. So that's how I found out why it was just bad. It's just the CPU and the VIC chip, which is completely inadequate for that. So next computer is the NEC PC88. Now, unlike the C64, well, it has like the Z80 processor, but it has a much bigger resolution. So 8 colors by 640 by 200. Despite that, I kid you not, despite the much larger amount of stuff to update, because I believe the video RAM was like 16 kilobytes big. No, I think it was 32 kilobytes large. Uh, yes, I believe it was 32 kilobytes large. So let me check on that real quick. So I'll show you the code for it. Um, so yeah, this is how the NEC PC88 code looks like. And you can see that in game, I'm actually not using the blue plane. I'm actually using the red and green plane, because if I were to use all 3 planes, that would be actually 48 kilobytes of graphics. So this computer is a bit particular, but unlike the other computers, it's actually quite intelligent here. So, or should I say smart? Uh, the video RAM portion, it only gets mapped to the upper RAM portion of the memory, and it only also maps. It is also planar based, so you get a red plane, a green plane, and a blue plane as well. And this is how, by combining the 3 planes, you get 8 colors, and each plane is 16 kilobytes large. And yeah, because of this design, I was able to compress my graphics and update them on the fly. Now you may wonder, well, what is this about? What is like LZ48? Well, I saw like a benchmark online that was testing a bunch of decompression algorithm on the Z80 platform, and they found that the LZ48 was the fastest algorithm for the Z80. So once I gave it a try on the NEC PC88, and sure enough, compared to like a LZSA1, this one was even faster. The compression ratios were not as good, but they were quite close, I would say. Certainly good enough for like, I mean, like the to give you an idea, each plane went from 16 kilobytes to 2 kilobytes instead. So it was a lot better, and could have done it better, I guess, but really I think this is as far as it would go. Now, initially I was confused. I thought that I was using the V2 mode. However, the V2 mode allows you to remap the palette and colors, but that's the only difference. So V1, you get 8 colors that are fixed, and V2 it's the same except that you can remap the colors, the 8 colors that you have on hand. And yeah, I mean, this computer, once I figured that out, it was quite straightforward. I did have to read like the Z88 DK functions, because I couldn't figure out the planner system at first. This code right here, these 2 lines, it took me a while to figure that out actually. But once you know how to do that right here, then it's easy enough. And there is also a PC speaker which the Z88 DK does support. I was considering supporting VGM music on there, but I couldn't find much documentation about that, so I ended up just sticking with the 1-bit sound effects and stuff. So next is the NEC PC88. So this one comes in multiple configurations. So actually it was released at the same time as this one, but it was much more expensive. And it also had similar graphics as the PC88. So for a while, most people went with this one. But this one, eventually in 1985, they upgraded the computer. First, they doubled the colors to 16 colors. They also made the resolution higher. So instead of 640 by 200, we get 640 by 400. And NEC also started to release sound card upgrades for this computer. To be fair, they also did it for the PC88, but they also started to do it also for the PC88, and that's how this computer pretty much displaced this one. And we also have a lot more memory, and the CPUs are 16 bits this time, so pretty nice to see. And like the PC88, it is also planner based. The underlying system is DOS. On the PC88, it was something called N88 Basic. So it was more like a basic interpreter rather than an operating system or even a kernel for that matter. So here's the code for the PC98. So as you can see here, I'm using Open Wacom because this is for real mode. And I am using LZSA for compressing the graphics in-game. And you may notice that I'm also using the PMD sound driver. So PMD has been recently open sourced. by the Japanese creator of it. And PMD is basically how it works is, I'm going to show you the PMD related code actually, because it's quite interesting. I think it's this one. Yes. So first of all, you check if there is the PMD vector address and stuff, if it's even loaded into memory, and we check its signature. If it is valid, then you can call the music driver like so at interrupt 60. And then once you've called the music driver, well, you can do stuff like stop song, get the song buffer address like I do here. Then you load the music data onto the buffer, and then you simply call the music driver again to simply tell it to play. So quite straightforward. This bit in particular, though, it was the most difficult part to figure out, because on like real mode stuff, you have to deal with segmentation and offset, and that pisses me off so bad. It is just a quirk of like the 16 bits Intel processors that thankfully they got rid of with like the 32 bits processor. But you know, once I figured that out, it was quite straightforward, and the same can be said for like the sound effects. Now the sound effects, it's done a bit weirdly. You don't load the music at an offset. You before you even load the executable, you call another executable to load the PCM stuff onto memory, and then you can do stuff like this. Now this is a bit misleading because I said that it starts at index 1 but not 0. However, I discovered that index 0 also worked. So yeah, a bit misleading here. Besides that, not much to say really. If you want to see the full source code, it's on my GitHub. Next, we have the NEC PC9821. So this was back when DOS PCs started to have SVGA graphics. So NEC did a slight upgrade by still having the same resolution as before, but this time we get 256 colors. And the good news, it is also completely linear, so it is not planar based. A few computers in this line also supported a planar mode at 8 bpp, but it was not all of the computers. So most games just ended up sticking with the linear based mode. And some PC9821 also came with an integrated sound chip, but others, such as the one that I actually bought, it's actually the XE7 model. This one only came with the PC speaker, I believe, so no sound. So NEC expected you to buy a sound card to put it into your computer, so extremely annoying to see. So for this version, because I forgot to mention that the PC98 also had PCM playback thanks to the PMD driver that I mentioned. But for this version, I extended it to also support the basic 24 sound card, which is just PSG based basically. And you can do a PCM playback on that. As you can see here, it is quite different from the Oric code. It's a lot more variables, I would say. It's actually based on a DOS library that I was working on, and the intention was to eventually add support to my DOS library, but I only ended up partially doing that. So, and I also did not fully update it to that. So yeah, the PC98 and stuff, the cool thing about it is that they also have a text layer that is separate from the main graphics layer. So you can have text on top of the graphics, and the text will not slow down the graphical operations. You also have something called the I actually forgot the name of the accelerator chip. There was the GDC and the EGC. So let me show you here. I actually had some code for like the EGC right here for like doing stuff like copying across VRAM pages, and also doing like blank pixel copy. But I've been told that in my case this will be a bad idea and that I should just do it raw, especially in the case of the PC9821. But I still had the code uncommented if anyone was potentially interested. So next computer, DOS. So this version took me a month at least, unlike the other PCs. The PC98 and stuff, they took me at least a week. But these, they took me a month due to the sheer amount of graphics card and sound cards to actually support. I mean, it's just insane. So yeah, so all of the stuff that you see here, I had to support it. And the most painful part was probably the sound cards. Now I said that I wrote like OPL2 and General MIDI. That was for the music, because for the sound I also supported a PC speaker, the Adlib also for sound using the PCM as 6-bit tricks, and as also the Sound Blaster. So all of that junk that took me a lot of time. But if you take out my code right here, it may not seem obvious at first. Well, I guess it is in sort of a way. First of all, I have this alternative text right here. This is actually for the PC Junior and the Tandy, because if you use like the lower PC Junior and Tandy resolution, this one right here, well, the text it ends up being too long, so I had to make it shorter. And I also had to support stuff like VGA, EGA, CGA composite, CGA black and white, CGA black and white inverted, Hercules in color, and as well as numerous high resolution and mode X support, including stuff like 640 by 400 VGA and 800 by 600 16 colors as well, which that's what I would recommend that you use under most circumstances if you want to run this game with like the 386 version. Otherwise, if you're stuck with like if you want to just run the real mode version, you can just run the VGA version of it, and that will be fine. And yeah, this version caused me a lot of trouble. It was very, very annoying. And as you can see here, I even added support for like PCM playback on the Tandy PSG sound chip, the PC speaker, the Adlib, and the Sound Blaster. Now, let me show you actually the PC speaker code. This right here, it does 1-bit PCM playback on the PC speaker. So we have an interrupt, and we basically go through the sample, and we do it on an 8-bit basis. So this right here, we only increase like the index of it once we actually went through each bit. If so, we can move on to the next bytes. So yeah, that's how I do 1-bit PCM playback on this computer. And don't forget to actually save the old interrupts and load it back once you're done with the device, because otherwise you're gonna have a lot of trouble. And make sure to also change the R and Q frequency and stuff accordingly. You may want to change this bits accordingly if you want to have higher quality and stuff like that. So yeah, the DOS version was very annoying to work with. I ended up not putting this version on a floppy disk because it ended up being too large, unfortunately. Uh, let's take a look. I think it was the final port of it. No, it's the second last. So the Atari STE. So my port of the game actually supports both. So the STE, the only difference is that you can select from a larger color palette, and you have something called DMA sound, which this game does support. And the Atari ST originally came with 512 kilobytes of RAM, although in some markets it came with even less than that. But most people, I mean, games were pretty much expecting that the Atari ST came with 512 kilobytes, basically. So for the colors, it's 16 colors at 320 by 200. So it's kind of well, it was similar, I would say, to the Amiga, but not really. The Amiga had like the little chip and the copper and stuff like that. The Atari ST was quite boring by comparison. You just had the screen, you just had the buffer to work with, and that's pretty much it. Uh, let me show you the code. So again, I'm actually reusing the sound files from the DOS version or like the PSG stuff, because the sound shape in the Atari ST is actually almost the same as the one in the 10D1000 computer. I also have sound files for like DMA sound. So what it does is basically if it detects that the computer is an STE computer, it switches to using DMA sound. Otherwise, it uses a PSG sound. And that ensures that it should work on most computers. So the way that you do graphics on the Atari ST is that you first call this function right here, logbase, which gives you like the physical address. Well, actually, it's this one, but you get the virtual and physical address of the screen, and then you can do a MAME copy to that or decompress the graphics to that, as I'm doing here. But in game, I'm actually doing a MAME copy, I believe. Yes, I am doing a MAME copy, and I actually forgot the reason why I did not compress the frames. Don't I think the computer was fast enough, I believe, but I think it was something related to the text and how I was drawing it. I'm not sure. I actually forgot why. I mean, I've coded like this version for like a week ago, and I already forgot. Stupid me. Uh, so here's the PSG PCM code. So unlike on the IBM computers, it is a bit stupid. I didn't bother with like the interrupt code as I did on the IBM. I'm not familiar with the Atari ST, unfortunately, so I just ended up putting it in the loop. I was kind of afraid that actually it wouldn't be fast enough for like PCM playback with the PSG, because it is quite CPU intensive, unlike the Atari DMA stuff. By comparison, if you look at my DMA code, it is quite simple. It's actually just a bunch of assembly functions that I may call to, and yeah, it is straightforward enough. So the Atari ST version was quite easy to do actually, but you should play my stupid game on the SCE if possible. The last one actually was very annoying to work with. This was for Vantage Max, so the Macintosh 512 kilobytes, and also the Macintosh Plus. The annoying thing actually was not actually the display, I eventually figured that part out, but it was actually the sound portion. To this day, I still couldn't figure out how to use the stupid sound driver because it makes no fucking sense. I looked it up on like some the few source code that is available, and I just couldn't get it to work. I only got symbol beeps to work, and that's it. So I ended up just using like the sysbeep function, and that's it. So that's what I ended up doing. As for the keyboard keys, I just ended up using a function called get keys. That works fine, but if you want to detect multiple key presses, this will not be good enough. But in my case, it was, so I went with that. The button that you see here, it's for detecting a mouse click, actually, so quite straightforward. I believe it is actually provided as part of the OS. Yeah, I mean, if you take a look at my stuff right here, you get a base pointer which points to the quick draw pointer. So for this right here, no, not this one, this right here. This is the base address that you would write to display graphics with, but if you have like a different resolution than expected, you can have an off-screen memory that you can allocate and then display that with something called copy bits, and then that will center the graphics on screen once you do all of that. So yeah, that was the last port of the game that I made. So in total, I ported this game to like 20 platforms. I've learned quite a lot, to be honest, and in a lot of these projects, I've used ChatGPT a lot. I did get help in some cases for like I believe it was like the Commodore 64, which I did get help, and also the IBM DOS version. I got help for like the 10D graphics. But other than that, most of the time it was just asking ChatGPT and sending documentation to ChatGPT, and it helped me with that. On a fun note, let me show you also this. So this is a Python script for like converting like the now the CGA bit is a bit misleading here, so I'm just gonna change it to Mac. But yeah, I basically gave a plotting function to ChatGPT, and it came up with that. So it was quite simple now. But the plotting function itself, so how do I do it? So basically, I tell ChatGPT, well, if I do a mem set to the screen, it gives me 8 white pixels if I set the value to 256. And ChatGPT is smart enough to figure out that it is basically a linear based one bit display, and that's how I ended up with it. Did take me a couple of tries though, because initially I didn't get that, so I should mention that. But yeah, I also did that as well for the multiple DOS stuff. So for example, well, MCGA is simple enough, so that wasn't the hardest part. But something like Hercules, for example, that was a lot more difficult to figure out. I wouldn't have done this on my own, this stuff right here. Same thing for like the 10D mode. That one was difficult. Now there was this custom pilot stuff, but it's not used here. And even like the VGA planner mode, this one right here, I wouldn't have figured that out either. So yeah, all of my code is on my GitHub if you want to know more. So thank you for watching, guys, and bye.